The area of a polar sector is given by the formula that's on the screen. It looks a little bit mysterious, but it's really not too bad. The idea is if I have a region given by some function r as a function of theta, with a theta equals theta 1 0 starting and theta equals theta 1 stopping, and I want to find the area of this sector, this formula is the one that does the job. You can tell you've got the right formula because it matches the area of a circle. Because an area of a circle is just r is equal to capital R constant. And then 0 is between, or theta is between 0 and 2 pi. And when you go ahead and find the area, let's use that formula, 0 to 2 pi, capital R squared, the constant. Well, what do you get? Well, you get capital R squared over 2, theta between 0 and 2 pi, and right away you'll see that we get pi capital R squared. So that's how the formula works. So the 1/2 in the formula, this 1/2, is due to the fact that our radians go between 0 and 2 pi. Okay, let's try a little bit more substantial formula. So find the area of the cardioid. R is 5, 1 minus cosine of theta. And without any limits on theta, it'll go between 0 and 2 pi. If we want to plot this cardioid, it's quick enough to tell. Because if I put in theta equals 0, cosine of 0 is 1, and so that will put me 1 minus 1 is 0, and that'll put me right on the origin. As I increase my theta, the cosine increases, so 1 minus the cosine will start increasing, and so it'll kind of go up as my theta goes around. At theta equals pi over 2, my cosine is 0, so at pi over 2, that's the vertical line. My cosine is 0, and so this right here is 5 units. And it keeps getting a little bit bigger from there. And finally, when I get to theta equals pi, I get 10 units out. And then it looks symmetric. So that's the cardioid. So we want to find the area of that cardioid. Okay, well, let's use the formula. Zero to 2 pi r squared d theta zero to 2 pi 5 squared 1 minus cosine of theta squared d theta. So that means my area then is 25 over 2, 0 to 2 pi. Let's multiply out the contents here. And at this stage of the game, it's useful to have a trig identity. That trig identity allows you to rewrite the cosine squared in terms of cosine 2 theta. So let's use that trig identity. So that's a nice little trig identity. Assembling before we want to take the integral here. It's 3/2 minus 2 cosine theta plus 1/2 cosine 2 theta. go ahead and integrate that. We have theta minus 2 sine theta plus 1/4 sine 2 theta between 0 and 2 pi. Now at 0 and 2 pi, the sines are both 0, and so we are left with 25 times 3 times 2 pi over 4, or, well, I guess it is. I've got 1 factor of 2 there, so this is 125 pi over 2. If you want to know what that is numerically, that's about 117.8 units. All right. Now, it's always good to check your work. It's even better to check your work physically. So let's see if this really works out. If this is, instead of an area, this were a mass. So let's make this out of wood with a density of 0.22 grams per square centimeter. These are units squared. So if all my units were in centimeters, so 117.8 square centimeters times 0.22 grams per centimeter squared, that's about 25.9 grams. So let's go ahead and make a wooden cardioid and measure its mass and see how that is. See how close we get. So really the thing to do is to write a computer program that will render the cardioid nice and precisely, print it out on a piece of paper so that we can transfer it to the piece of wood, cut out the cardioid from the piece of paper, glue it to the piece of wood, and let the glue dry, and finally cut it out of the piece of wood. Then we'll have a nice cardioid model that's very precise and accurate and ready for measuring. Okay, so we've cut our cardioid out of a piece of wood, and our estimate is that its mass should be 25.9 grams based on its area and the density of the wood. Let's see how well we did. 26.1, pretty darn close to 25.9 grams. Guess the math works.